Hello everyone, welcome back to SHR Trinity. In today's video, we are continuing our machine learning interview questions series. This is part 4, where we will dive deep into advanced machine learning concepts, covering questions 31 to 40. We will explore clustering, dimensionality reduction, hyperparameter tuning, and specialized domains like recommendation engines and time series forecasting. Let's study these advanced topics in detail. Before we dive into the questions, let's look at what we'll be covering in this video. We will discuss advanced machine learning concepts. We'll start with clustering, k-means, and hierarchical clustering, explore dimensionality reduction, explain principal component analysis, cover hyperparameter tuning, compare grid search versus random search, explain model selection, recommendation systems, and time series forecasting. Question 31. What is clustering? Clustering is a core unsupervised machine learning task. Unlike supervised learning, there are no target labels or ground truth outputs provided in the training data. Instead, the clustering algorithm must analyze the inherent structure and features of the dataset to group similar data instances together. The mathematical objective is twofold. First, to maximize interclass similarity, meaning data points assigned to the same cluster should be as close or similar to each other as possible. Second, to minimize interclass similarity, meaning different clusters should be as distinct and far apart from each other as possible. Common applications of clustering include customer segmentation for targeted marketing, anomaly detection to flag unusual behaviors, document grouping, and image compression. Question 32. Explain k-means clustering. K-means is a highly popular centroid-based, iterative clustering algorithm. The user must predefine the number of clusters, k. The algorithm operates in 4 sequential steps. First, initialization, where k points are randomly selected in the feature space as the initial cluster centers, or centroids. Second, the assignment phase, where the algorithm calculates the distance from every data point to all k centroids, typically using Euclidean distance, and assigns each data point to its nearest centroid. Third, the update phase, where the centroid of each cluster is recomputed by calculating the mathematical average, or mean, of all data points currently assigned to that cluster. Fourth, iteration, where steps 2 and 3 repeat sequentially until convergence, which is when the centroids stop shifting their positions or a maximum iteration limit is reached. To find the optimal value of k, data scientists commonly use the elbow method, plotting the within-cluster sum of squared errors against different values of k and selecting the point where the rate of decrease drops sharply. Question 33. Explain hierarchical clustering. Hierarchical clustering is an unsupervised clustering algorithm that builds a nested hierarchy of clusters, represented visually as a tree-like diagram called a dendrogram. Unlike k-means, you do not need to specify the number of clusters beforehand. There are 2 main approaches. Agglomerative hierarchical clustering is a bottom-up approach. It starts by treating every single data point as an individual, independent cluster. In each subsequent step, the algorithm identifies and merges the closest pair of clusters. This process repeats until all data points are merged into a single, massive cluster. Divisive hierarchical clustering is a top-down approach. It starts with all data points in a single cluster and recursively splits it into smaller clusters. To measure the distance between clusters for merging or splitting, the algorithm uses linkage criteria. Single linkage checks the minimum distance between points, complete linkage checks the maximum distance, average linkage checks the mean distance, and Ward's method minimizes the variance within clusters. The dendrogram allows developers to visually cut the tree at a specific height to select the optimal number of clusters. Question 34. What is dimensionality reduction? In machine learning, as we add more features or columns to our dataset, the volume of the feature space increases exponentially. This causes the data points to become extremely sparse. This phenomenon is known as the curse of dimensionality. When data is sparse, models require significantly more data to generalize well, are highly prone to overfitting because they memorize noise, and suffer from slow training and execution speeds. Dimensionality reduction is the process of reducing the number of random variables under consideration. It is achieved through two main strategies. First, feature selection, where we keep a subset of the original columns and discard irrelevant or redundant ones, using methods like variance thresholding or correlation analysis. Second, feature extraction, where we project the high-dimensional features into a new, lower-dimensional coordinate space, combining features mathematically. Dimensionality reduction makes training faster, reduces model complexity, and allows us to visualize high-dimensional data in simple 2- or 3-dimensional plots. Question 35. Explain principal component analysis. Principal component analysis, or PCA, is a widely used unsupervised linear dimensionality reduction technique. PCA transforms a large set of correlated features into a smaller, uncorrelated set of features called principal components, while retaining as much of the original data's variance as possible. The algorithm calculates the covariance matrix of the scaled data to find its eigenvectors and eigenvalues. The eigenvectors represent the directions of the new coordinate axes, which are the principal components, and the eigenvalues represent the magnitude of variance captured along each direction. The first principal component is chosen along the direction of maximum variance. Each subsequent principal component is orthogonal, or completely perpendicular, to the previous components, ensuring they are entirely uncorrelated and free of redundant information. Look at the code on screen showing how scikit-learn implements PCA in a few lines. We import PCA, set n_components to 2, and apply fit_transform on our scaled features, then print the ratio of variance captured by each component. Question 36. What is hyperparameter tuning? In machine learning, it is crucial to distinguish between model parameters and hyperparameters. Model parameters are internal configurations that the algorithm learns automatically from the training data, such as weights in linear regression or split thresholds in decision trees. In contrast, hyperparameters are external configurations set by the developer before training begins. They control the behavior of the training algorithm and directly dictate model complexity. Examples include the learning rate in gradient descent, the number of estimators in a random forest, or the regularization strength C in support vector machines. Hyperparameter tuning is the systematic process of finding the optimal combination of these settings that minimizes generalization error on unseen validation data, balancing underfitting and overfitting. Question 37. Grid search versus random search. Look at the comparison table on screen. Grid search is an exhaustive search method where the developer defines a specific grid of hyperparameter values, and the algorithm trains and evaluates a model for every single possible combination in that grid. While it is guaranteed to find the absolute best combination in the defined space, its computational cost is extremely high and scales exponentially with the number of parameters. Random search, on the other hand, evaluates a random selection of hyperparameter combinations sampled from a statistical distribution over a fixed number of iterations. Random search is far more computationally efficient. Since it doesn't get stuck searching closely clustered redundant points, it has a higher probability of discovering optimal values on a given budget, making it the preferred choice for high-dimensional hyperparameter optimization. Question 38. What is model selection? Model selection is the phase in a machine learning project where we choose the best performing model from a set of candidate algorithms. According to the no free lunch theorem, no single machine learning algorithm is guaranteed to outperform all others on every single task. An algorithm that works perfectly on text classification might fail completely on tabular financial data. During model selection, we train multiple diverse candidate algorithms, such as logistic regression, random forests, and XGBoost, and evaluate their performance using cross-validation on a consistent validation dataset. We must balance trade-offs between. Question 39. What are recommendation systems? Recommendation systems are specialized algorithms designed to predict user preferences and suggest items that users are likely to interact with or purchase. There are three main approaches. First, collaborative filtering, which relies entirely on historical user-item interactions, suggesting items based on the behavior of similar users, or recommending items that are frequently bought together. Second, content-based filtering, which recommends items based on the descriptive features of the items themselves, mapping them against a profile of what the user liked in the past. Third, hybrid systems, which combine both approaches to eliminate their individual limitations. A major challenge in recommendation systems is the cold start problem, which occurs when a brand new user or item enters the system, providing no historical data for collaborative filtering. Question 40. What is time series forecasting? Time series forecasting involves predicting future values based on historical data points collected sequentially over time. Unlike standard tabular data, time series observations are not independent and identically distributed. Therefore, random train test splits are not allowed. We must preserve temporal ordering. A time series has three main components: trend, which is the long-term upward or downward direction, seasonality, representing repetitive cycles over fixed intervals, and noise, which is random variance. The core mathematical concept is autocorrelation, measuring how a variable correlates with its own past values, known as lags. We use statistical models like ARIMA, regression libraries like Prophet, or deep learning architectures like LSTM to forecast future values. Thank you for watching. If you found this video useful, please subscribe to SHR Trinity for more videos, and click the like and share buttons. Stay tuned for Part 5, where we will cover expert level and real-world scenarios. If you are interested in attending our live training sessions or have any inquiries, all our contact details are displayed right here on screen and are also available in the video description below. Feel free to reach out to us. We would love to have you as part of the SHR Trinity learning community.